So in this lesson, we're going to be talking about acids and bases. First of all, what they are. Secondly, how they actually separate themselves. And then thirdly, how acids and bases work together to produce a reaction. So to start off with, we need to identify what an actual acid is. And just to go through it one more time, is that an acid is any sort of chemical that starts with hydrogen. Water, H2O, is the exception. But any other chemical formula, if you see an H in front, you know it's an acid. So here we have hydrochloric acid and hydrofluoric acid, and then many of you have heard of sulfuric acid before as well. We won't go into details of why this one is called hydrochloric acid and this one sulfuric acid as opposed to the hydrosulfuric acid, but there are some rules. And at this point, we'll just sort of identify them. I will identify them for you. But the key idea with an acid is, particularly a strong acid, it is that if you place this acid into water, it will separate itself into the hydrogen and chloride. This is very similar to the ionic compounds that we've worked with in the past. So, for example, hydrogen fluoride will separate itself from its anion, being the hydrogen, and the fluorine. So it sort of like, again, acts like an ionic compound. For this one, sulfuric acid, I just thought I'd want to just draw out what that looks like. So if you take sulfuric acid in a beaker, and if I were to add water, it would actually separate into its hydrogens and to the sulfate, okay? And you notice that in this case I have a 2 here because sulfate, if you look at your polyatomic chart, has a -2 charge. The hydrogen has +1. To have those equal 0, we want to make sure that we have 2 hydrogens to cancel out those charges. So in this case, let's just take a look at what that actually looks like in our beaker. So if you remember, water is a polar molecule. It is in this shape. You have your positive sides and you have the partial negative side because of its polarity. And when we talked about anything being dissolved or aqueous, we talked about how intermolecular forces are attracted differently depending on the positive or negative charge. And hopefully most of you will remember that this hydrogen, which has a positive charge, is going to be attracted to the oxygen, which has the negative charge. And just to simplify my drawing, I usually make it into just a little angle. And so in this case, the hydrogen is going to be attracted to the oxygen side of water. And so when we actually look at this specifically of how this disassociates, we're actually going to write it in a different way than we normally do. And the reason is that here we have our hydrochloric acid. We're going to actually write it so that it looks something like this. So we say plus H2O. Now the reason I do plus H2O is for this reason here specifically, is that what happens is that this hydrogen is going to be attracted to the oxygen side of this so that the molecule, like I said, remember it is attracted to the oxygen side, that this molecule actually changes the water to be what is called H3O. So this is why we actually record this. And so why is it H3O? Again, this is an attraction. We have 3 hydrogens and 1 oxygen. I give it a plus charge because it actually does have a plus charge. And I write down aqueous and then have the other just be by itself. So whenever I'm looking at acids and wanting to break down the equation to what we call more or less the Ionic Equation, we will include water to have the hydronium, that's this H that's from here, that's attached to the water to become HCl. So I actually, to be more accurate, I've noticed that I'm using different substances. I should have put H2SO4. And in this case, you're going to have the same situation happening, only in this case you have two hydroniums being made. All right? So you could also, you might see it as this here, where you just simply have it working out where you have H plus H2O becoming hydronium. The rest of them are spectator ions, and so we just have that be our net ionic equation. So either one is something you'll see. And I'll tell you specifically what it is that I'm looking for. So with that said, specifically, this is what the homework is going to be asking you to do. It's going to give you a chemical. It's going to ask you to combine it with water. Better said, it'll give you an acid so that you can make the hydronium with the anion. So the same format applies to bases. Bases, keep in mind, they end with OH. And while that's not completely true, for our purposes it is. And so something like sodium hydroxide is a base. Lithium hydroxide is a base. And it's the same story as it is with acids. And that the base disassociates itself with its cation. So in this case, let's do sodium hydroxide. You're going to have a sodium hydroxide and an OH. Okay, sodium hydroxide and an OH. And the easier it is for these to separate, the stronger the base. So strong base equals easily separating the cation with the anion. Okay? Ones that are weak bases actually don't separate so easily. So you notice that this solution has a lot of OH in it. So we're going to show that also in a reaction of how it disassociates. And this one is a little bit different in that it's much easier, in that you literally just separate them. You have NaOH, and this one could be an aqueous form, and it separates just to be the Na plus the OH minus. Okay? So in this case, you do not add water, whereas with the acid, you do add water. And the only reason you're doing that is to show that actually a hydronium, that's that H2O with the H attached to it, is formed. For this one here, you don't actually have any new substances being formed. All right, so this is how you would identify acids and bases. Keep in mind a base ends with OH and acid starts with H. This is how you would write a base when it actually disassociates. So whenever it asks you to, for your homework, to write an equation of the formation of ions, this is what you're going to write. And the last part that I want to talk about is what happens when these two combine. Okay, so firstly, you need to identify if it's an acid-base reaction. So I notice I have a compound starting with an H. I recognize that's an acid. And then I see that this one is ending with an OH, so I recognize that's a base. Clearly, this is an acid-base reaction. The other big hint is that it always will make water, okay? And these are very similar to the precipitate reactions. As you notice, you more or less have what we call a double replacement, where the Na goes to the Cl and the H goes to the OH. And so you have a reaction, if I were to write it simply as we've always done, where NaCl, aqueous, and here's that OH going to the OH, which is a liquid form, that's my L, which is the same thing as H2O. Okay? So this is how you can neutralize something so that you have a water reaction as a product. Okay? So acids and bases, when you combine them, you can neutralize them in that they form water. So this is a neutralization reaction. So in all of this here, one of the things that I want to talk a little bit about is why do we care? Like, who cares about all of these things of why acids dissociate? Well, one of the big issues that we're dealing with in our ecosystem right now is the fact that we've got a lot of carbon dioxide being spewed out by industry, by cars, by factories. And one of the things we had talked about a few months ago was how this carbon dioxide actually interacts with ocean water to create something that is H2CO3. So instantly, as you see this compound, you see, oh, it starts with an H. This clearly is an acid. So what we're doing is that water, ocean water, and the carbon dioxide is making acids into the ocean. And you notice that this is actually a reaction that is both a forward and a reverse reaction. We've been talking a little bit about that. So we've got as we're adding more and more carbon dioxide, what's happening is that we have a shift forward with this equation that more and more acid is being made, that eventually our oceans are becoming more and more acidic, that they can't actually supply life. So as environmentalists, we want to stop the carbon dioxide to come out, and so maybe we are going to make very conscious moves of driving less, of having less industry, in which case we reduce the amount of carbon dioxide. So from what you remember from that equilibrium system, what happens when you have less carbon dioxide? Which way does it shift? Well, it shifts this way, meaning that the acid in the ocean is actually going to more or less do a reverse reaction where we have carbon dioxide coming back out into the ocean, from the ocean into the atmosphere. So we're going to have these high levels of CO2. Does that mean we should not reduce our emissions of CO2? No, of course we do, because we're shifting the equilibrium this way. We still are going to, over time, if we keep on reducing it, we're going to reduce the acidity of our ocean. And if we keep on pulling that carbon dioxide out, hopefully, eventually, not only will our oceans not be so acidic anymore, but we can also pull the carbon dioxide out. So that ends our acid and base lecture.